The subject of the 2021 EPD Distinguished Lecture is Ferronickel, Thermodynamics, Chemistry and Economics. My name is Rodney Jones and I'm a consulting chemical engineer and metallurgist with over 35 years of working in pyrometallurgy at Mintec in South Africa. I still have a part-time appointment there and also at the University of the Witwatersrand in Johannesburg. I am a past president and an honorary life fellow of the Southern African Institute of Mining and Metallurgy. Before we can talk about ferronickel, we need to talk about nickel first. Nickel is a metal that has become essential to many aspects of our daily lives, from tableware and kitchen utensils to medical equipment, aircraft, coins, and batteries. Nickel is a silvery white metal that is both hard and ductile and has a melting point of 1455 degrees Celsius. It is resistant to corrosion and high temperatures and confers these properties to alloys that it's a constituent of. Long before nickel was isolated, an alloy of copper nickel zinc was produced in China called pak tong, or white copper, nowadays known as nickel silver. But nickel was only isolated and recognized as a distinct metal by the Swedish mineralogist and chemist Axel Cronstedt in 1751. Cronstedt is considered a founder of modern mineralogy and mineral analysis. He introduced the use of a blowpipe as a tool for mineralogists and proposed a mineral classification system or taxonomy based on chemical analysis. At the age of around 40, Cronstedt bought an iron foundry and soon after that turned to gardening, saying that roses gave more reward than minerals, which were sorely lacking in monetary return. You can take issue with that statement if you like, but perhaps it keeps our feet on the ground as we discuss other metallurgical matters. Cronstedt died at the young age of 42. So, how economically important is nickel? This table shows a series of major metals and a few precious metals with their production tonnages and their contained values. So you can see that 2.6 million tons of nickel was produced in 2019, representing a value of over 36 billion US dollars. The amount is perhaps small relative to the amount of steel that is produced in the world, and maybe a tenth of the amount of copper, which is a comparable metal, but nevertheless, nickel is 8th by tonnage and 5th by value. So it's fair to say that nickel is both valuable and common. The Earth's core consists mainly of a nickel-iron alloy, but the concentration of nickel in the Earth's crust is only 80 parts per million. The world's nickel resources, those with reasonable prospects for eventual economic extraction in classical ore deposits, are currently estimated at almost 300 million metric tons, about 120 of these as sulfidic materials and about 180 lateritic. Recent estimates indicate more than a further 290 million tons of nickel contained in manganese nodules on the deep sea floor. World nickel reserves, those that are economically mineable right now, are currently estimated at 94 million tons by the US Geological Survey, with about 2.5 million tons being mined annually. Reserve estimates vary with time as economic viability depends on mining, processing, marketing, legal, environmental, infrastructure, social, and governmental factors. Nearly 80% of all nickel historically mined was extracted over the past 3 decades. The global efficiency of recycling nickel from end-of-life products for 2015 was 68%, amongst the highest recycling efficiencies for the metals industry. The table here shows the nickel resources, reserves, and mine production by country for all the countries leading in nickel in the world. The resources are listed by sulfidic and lateritic components and are ordered according to the combined total of those resources in the ground. The reserves are also listed. Those are the ones that are currently economically mineable. And then the mine production figures in kilotons for the year of 2020 are listed in the column on the right. Highlighted in red are the ones that lead the pack in terms of laterite ore production, and shown in blue are the highest figures for sulfidic production. So our leading producers of laterite ore are Indonesia, Philippines, and New Caledonia. The figure shown here illustrates world nickel production between 1900 and 2020. And you can certainly see quite incredible growth over that time period. Between 1980 and 2015, a study by the Geological Survey in the US looked at world nickel production and realized that it increased by 3.1% annually. Just looking at this figure in front of us, just worth reiterating that nearly 80% of all the nickel historically mined was extracted over the past 3 decades. The nickel price is shown for that same time period. And of course, that has varied quite considerably over more than a century. The figures shown here represent the nominal cash settlement prices for LME cathodes of 99.8% nickel. It's also important to note that the figures have been tabulated as annual averages to remove some of the fluctuations. However, you can see that nickel prices certainly fluctuate an awful lot. If we correct the nominal nickel prices to real prices, taking into account the effects of inflation, as shown in the graph here, some of the things that really still stand out are the peaks in 1988 and 2007. Of course, that one followed by the crash of 2008 going into 2009. However, if we extend that data series even earlier, and we look at figures from 1850, we can see that the peak in 1873 makes the peaks of 1988 and 2007 look like minor fluctuations. So what happened in 1873? Well, the usefulness of nickel in alloy steels was recognized in 1870s, pushing up demand significantly. But the mining of nickel laterite ore in New Caledonia began in 1875, and that brought down the costs radically. Nickel demand is dominated by stainless steel, which accounts for about 70% of the first use market share. There is 8% that goes to alloy steels and castings, another 8% that goes to non-ferrous or nickel-based or copper-based alloys, 8% to plating, 5% to batteries, of which we'll talk more later. And we can also classify the distribution by end use in 31% engineering, 22% metal goods, with the remainder going to building and construction, transport, electronics, etc. Rapid growth is anticipated for nickel in batteries, but off a small base, perhaps reaching over 30% over the next decade. Looking now at stainless steel, the ultimate purpose for much of the nickel that is mined, in 2019, global stainless steel production was around 52 million tons, having doubled over the previous decade. Stainless steel has grown faster than other major metals, as can be seen by the compound annual growth rate listed for a number of metals on the bottom left, showing that the growth rate for stainless steel is 5.6% per annum, which really is way in excess of that of other comparable metals. The minerals boom of the early 2000s was driven primarily by the urbanization of China, which became the leading stainless steel producer in 2006. The figure on the bottom left shows a curve in red illustrating China's share of global production of nickel. From 1994, it was almost nothing, to current figures where China produces more than half of the world's stainless steel, with demand growing at over 4% per annum. The figure on the right indicates how China has grown in consumption of nickel relative to many other comparable countries. The other focus area of interest for nickel is, of course, the lithium-ion batteries. Shown in the photograph here is John Be Good Enough, and he certainly was. He's now 98 years old and is the oldest recipient of a Nobel Prize. He won the Nobel Prize for Chemistry in 2019 as one of the inventors of the lithium-ion battery, which made possible the era of portable electronic devices as well as battery electric vehicles. These batteries are expected to require vast quantities of metals, such as nickel. Climate change and the resulting governmental regulation has sped up the transition to electric vehicles, and lithium-ion batteries for these vehicles use nickel extensively. The NCM batteries, that's nickel, cobalt, manganese, most commonly in an 8:1:1 ratio, and the NCA, or nickel, cobalt, aluminium cathode materials, are dominant because of safety and energy capacity considerations. There is a strong preference for higher nickel intensity rather than the expensive and rather controversial cobalt. Nickel consumption from the battery sector was nearly 100 kilotons in 2017, at that stage about 5% of total consumption. And according to some studies, this is expected to grow to more than 440 kilotons of nickel by 2025. Questions about the availability of nickel are less about whether there is enough in the ground, but more about whether there is enough production capacity immediately available to meet such a rapid increase in demand. One of the driving forces behind the use of nickel in batteries for electric vehicles is Elon Musk, who incidentally grew up about 5 kilometers away from where I live. A Tesla Model 3 car contains about 30 kilograms of nickel, and an average Tesla car uses perhaps 45 kilograms of nickel in the NCA and NCM 811 batteries we've spoken about. Tesla wants to produce about 20 million vehicles per year by 2030 and will need some 750 kilotons per annum of nickel, about 30% of global production, to achieve this. In July 2020, Elon Musk said to nickel producers, "Please mine more nickel and don't wait for nickel to go back to some high point that you experienced some 5 years ago. Tesla will give you a giant contract for a long period of time if you mine nickel efficiently and in an environmentally sensitive way." In February 2021, he said, "Nickel is our biggest concern for scaling lithium-ion cell production. That's why we are shifting standard range cars to an iron cathode, plenty of iron and lithium." He's of course referring to the LFP or lithium iron phosphate batteries that do not have the capacity of nickel batteries. Tesla decided in March 2021 to become a technical partner in Goro nickel mine in New Caledonia and will buy nickel from that mine. Perhaps this goes to show the fickleness of the nickel industry, or should that be the nickelness of the fickle industry? But of course, nickel prices still depend much more currently on stainless steel demand than they do on batteries, but batteries are growing in importance. Now we shift our attention to nickel laterite, the source of material for ferronickel smelting. Laterites are formed by the weathering of ultramafic rocks close to the Earth's surface, which makes them relatively inexpensive to mine. The name laterite, from the Latin later, meaning a brick, is used to describe the weathering product of ferruginous rock exposed to strongly oxidizing and leaching conditions, usually in tropical and subtropical regions, or regions that had those conditions in geological ages gone by. This porous, clay-like rock comprises hydrated oxides of iron, aluminium, etc. Nickel leaches from the upper layers and subsequently precipitates in the lower layers, substituting NiO for MgO and FeO in the lattice of silicate and iron oxide minerals, respectively. It's very important to note that the major impurity in nickel laterite ores is in fact water. Mined laterite ore, being very porous, can hold a large content of free moisture, commonly 25 to 30%, going up to even 40% or more. In addition to this, chemically combined water, which requires temperatures of up to 800 degrees Celsius to drive off, can amount to as much as 15% based on the dry ore weight. Because of the quantity of water present, and because water requires so much energy to evaporate and heat up, it is clear that some pretreatment of the ore, at least drying and calcining, is required before smelting. Nickel laterite ores are typically evaluated according to their nickel content, nickel to iron ratio by mass, and their silica to magnesia ratios. The oxidized ores of nickel constitute by far the world's largest known reserves of this metal. The ores include the true laterites, in which the nickel oxide is intimately associated with limonitic iron oxide, and the silicate ores, which often contain the mineral garnierite. In 1865, Jules Garnier discovered large deposits of silicate ores in New Caledonia, a French possession in the Pacific. Mining was started in 1875, and this soon became the main source of nickel, the price falling within 3 years to about 1/3. So where does ferronickel fit into overall world nickel production? The split in nickel production between sulfide and laterite nickel ore sources has shifted from about 1/3 being from laterites in the 1980s to the about 70% from laterites in 2020, shown in the figure below. Nickel production from laterite ores is further subdivided between leaching of limonite and smelting of saprolite garnierite. The laterite smelting processes are further subdivided by alloy product into those containing nickel pig iron, containing, say, less than 15% nickel, and those producing ferronickel itself, ranging from 15 to about 40% nickel. Nickel pig iron, basically a low-grade ferronickel, has become popular only in the past decade. Our focus here is on ferronickel smelting, which produces around 600 kilotons per annum of contained nickel, representing about 23% of the overall world nickel production of 2.6 million tons per annum of nickel in 2019 figures. The first processing treatment for recovering nickel from laterites was developed in 1879 in New Caledonia, based on the iron blast furnace technology of the day. However, nowadays, almost all ferronickel production is based on the rotary kiln electric furnace, or RKEF, process. The schematic diagram here shows a highly simplified version of the flow sheet that is employed, where laterite ore is dried using a considerable amount of energy to drive off the surface water as steam. The solids are then put into another rotary kiln where energy and carbon, if pre-reduction is to take place, is added, and this drives off the chemically bound water at temperatures around 800 degrees Celsius. The center point of the process is the smelting furnace, operating at about 1600 degrees Celsius, where considerable amounts of electricity and some carbon are added to the laterite ore, producing a molten ferronickel alloy and vast quantities of ferronickel slag, which, it has to be said, contain significant amounts of energy, which is just really an opportunity for people to solve a very difficult problem of recovering some of that energy for the process in time to come. Refining then takes place of the molten alloy to drive off the small impurity quantities of silicon, carbon, sulfur, and phosphorus. And finally, typically water is used to granulate the molten alloy to produce ferronickel granules for the market. The technical part of my talk really is about how one can use thermodynamics to predict the grade recovery relationship in ferronickel smelting. It should be noted that George Box, the statistician, said that all models are wrong, but some are useful. And I hope that my contribution falls into the useful category. The smelting of laterite ores to produce ferronickel is essentially a series of chemical reactions involving reduction by carbon of the metal oxides. And so 4 of the metals are listed here, that of iron, nickel, cobalt, and chromium. We'll focus for the time being only on the nickel and iron, although the others can easily be incorporated and have been in the final working version of the model. If you combine the first 2 chemical reactions, you effectively result in the exchange reaction highlighted in blue between nickel oxide and iron, forming nickel and iron oxide. For this reaction, the equilibrium constant K can be found in tables at a particular temperature, and the equilibrium reaction, or the equilibrium equation, can be written in terms of the activities of the various reacting and product species, as well as the activity coefficients gamma and mole fractions X of those species. For convenience, we can lump together all of the activity coefficients into one mass term, just a number, called gamma. We add mass balance equations and definitions of recovery for both the iron and for the nickel, and finally result in a relationship between the recovery of nickel as a function of the recovery of iron and this number K gamma, just purely a number, dimensionless. The derivation of the equations can be found in the reference at the bottom of the screen for those interested. This equation can be plotted out for any of the metals, doesn't have to be only nickel. So for metal X, we have drawn a series of curves at various values of K gamma, and you can see that a straight line representing iron versus iron is K gamma, the 45-degree line in the middle of the curve, and the curves to the upper left represent the more noble and the least noble at the bottom right. K gamma can be calculated from equilibrium constant and activity coefficients, or it can usefully be fitted empirically simply with a single value that matches a recovery of nickel to recovery of iron under a set of conditions. This makes it quite a powerful predictive technique. The graph shown on the left is really the results of that thermodynamic approach, where we have plotted the recovery of nickel, cobalt, and chromium as a function of the recovery of iron. The values of K gamma chosen are based on experimental work, but could equally have been derived simply from a literature study. So if we, in our simplified model, we can assume for now just the nickel and iron components, and we've used this curve then to show the recovery of nickel using our equation. The value of K gamma that we have used for nickel is about 30. This could perhaps be as low as 20, and it should ideally be based on test work. We can simplify a fairly complex relationship to ultimately get our mass fraction of nickel in the alloy as a function of the recovery of nickel, the recovery of iron, and the iron to nickel ratio. So this will allow us to plot the grade recovery relationship for different values of the iron-nickel ratio in the feed materials. And this set of curves is now shown in the graph on the left-hand side. The relationship between nickel grade and recovery to the alloy depends on the iron to nickel ratio in the ore, and different color curves represent different values of this ratio in the feed. So the blue curve indicating iron to nickel of 8, we can see that it is possible to produce an alloy containing 25% nickel at a recovery of about 95%. But if we were to use an iron-rich ore, say with iron to nickel ratio of 20, an alloy containing 25% nickel could still be produced, but the recovery would be only about 80%. So now we have the tools to enable us to predict what that grade recovery relationship would look like, but it still remains for us to choose what ferronickel product grade we wish to manufacture. And it's possible by varying the amount of carbon fed to the same furnace to greatly vary the composition of the ferronickel alloy, all the way from the nickel pig irons with very low nickel, all the way up to a high-grade ferronickel alloy, up to about 40% nickel, say 60% iron. High iron reduction requires more carbon, more electrical energy, more refining of the increased impurities that result, and higher transport costs per ton of nickel. Generally, high reduction of iron, that is, a lower content of nickel in ferronickel, is favored when you have a high recovery of nickel being critical, as in the case of a custom smelter, and a reasonable payment is made for the additional iron in the ferronickel, and transport costs of the ferronickel to the market are low. The opposite conditions favor a higher nickel content in the ferronickel. Turning now to the slag, the slag Liquidus diagram shown here for the FeO, MgO, SiO2 system shows a remarkable alignment of the Liquidus temperature curves with the straight lines that represent constant values of silica to magnesia ratio. And so this ratio is really the most significant determinant of the slag behavior and properties. Tabulated here, we have the ferronickel production by country in 2017, listing the gross weight of the ferronickel products that are produced. We can see from this list that China and Indonesia lead the production and focus their attention primarily on nickel pig iron. And they can do this because the nickel pig iron smelters are very closely associated with stainless steel production facilities. All the other countries rely on the production of ferronickel per se. The final table, before I go to the concluding remarks, show a list of currently active ferronickel smelters, excluding the NPI producers. You can see the country in which these were produced, and the column on the right indicates the production capacity of each of the smelters in terms of kilotons per annum of contained nickel. For those smelters not currently producing at full capacity, their current production figures are shown in brackets in that same column. I've also indicated using red circles where the furnaces are circular furnaces, and with blue rectangles where furnaces are rectangular. A few observations come from this. One, that the circular furnaces outnumber the rectangular furnaces by a ratio of about 2 to 1. And the other notable feature is that very few producers have a single line of production. Nearly all of them have at least 2 or more furnaces in their smelters. The world is poised on the brink of some massive changes. Where we work, how we travel, given the current challenges that we face, such as a global pandemic and climate change. We are living in an exciting time of new developments and have the opportunity to shape the world for the better. The contributions that nickel, stainless steel materials, and batteries can make to a cleaner and kinder world are very significant. Think of buildings, food production, medical care, electric vehicles, and you will see what I mean. Nickel is an essential metal in our modern world. The challenge to ferronickel metallurgists will be to develop projects and devise processes that makes production of this valuable commodity more energy efficient and less carbon intensive. I'm sure you will be up to this challenge. Thank you.
Thank you very much, Rodney. As always, you lived up to our expectations of a great communicator. So I just received a photograph yesterday from Rodney. He received the plaque, basically the award, only recently, which I think is a very good indicator of the times we live in. Under pre-COVID, you would have traveled to TMS and received it in public. So I hope this is also a little part of us just reminding and celebrating with you what an awesome achievement this was. So congratulations again. So I'm sure you were watching the questions and answers, but there's a few interesting questions that's already popped up. Just see the questions here. As the age comes, we have to be careful what we read. So I see Valdini has been asking a few interesting questions. The first question he had for you is, do you have an opinion on how COVID impacted the ferronickel supply versus demand over the past year, and perhaps what do you think is the future?
Yeah, always hard to look into the future and really know what's going on, especially with these unprecedented times we've been going through in the past year and a half. I think the most recent figures in the production of nickel are shown in the curve, and I don't know if you remember seeing the curve and how much it grew over the last 100 years or so, and then how much it spiked and went up and down a little bit in the past decade, with all the changes around nickel pig iron, the growth in China, etc. But there is a noticeable downturn from 2019 to 2020, I suppose, dropping from about 2.6 million tons a year to 2.5 million tons a year. But what happens after that? I would expect to start seeing growth happening again, just in line with what's happening around the world in many other industries. And the fact that nickel is so reflective of stainless steel, which in turn really talks about major developments in the world, urbanization in China being the most prominent over the past couple of decades. I would fully expect to see things like that continuing to grow over the long term. So and of course, there's the big excitement around developments in battery technology as well. And I think that is going to have an impact, although what that impact is going to look like intrigues me, to be honest. If I look back to the 1873 spike that we saw, where effectively suddenly for the first time mankind realized the enormous potential of this element of nickel in producing significantly better alloys, steel alloys, that had been able to be produced up to that time. And so that created an enormous demand, enormous amount of excitement, enormous rises in price, only to find that people found a cheap way of mining it, and the price dropped dramatically after a few years as well. So will we see something similar happening in the battery technology world? You know, you look ahead maybe a half a year, which is about as much as we can do these days, and you think, yeah, we probably have got a fair idea as to which battery technologies are winning. But I would hesitate to make predictions over more than a year or so as to which technologies will ultimately prevail. Right now, it certainly looks as though the NCM, the nickel, cobalt manganese based batteries, the NCM 811, is the leading contender, because it's safe. You know, you've all read stories about about lithium-ion batteries bursting into flames, and nobody wants that. The more nickel you put into the battery, the safer it is, the greater the capacity that it has. So nickel is really in high demand as far as batteries go. Where the nickel comes from, I think is the sort of following question. I don't know if you want to tackle that one at all, Isabel, maybe just to read that out. All good, okay.
Sorry, my mute button got stuck, but yes,
all
please.
Right.
The
Sure.
next question, which grades of nickel are most common in batteries applications downstream? Do you think this is expected to change in the next near future, or technology leaps?
Yeah, so just to maybe expand a little bit on the downstream processing of nickel. Effectively, nickel as a commodity is divided into two classes, one being class 1, which is effectively high grade pure metallic nickel. Class 2, which would be the lower grades, such as those alloyed with iron, ferronickel, nickel pig iron, etc. Right at the moment, there's a huge demand for class 1 nickel for battery use. And effectively, you have to go from nickel metal to nickel sulfate, more specifically nickel high purity nickel sulfate hexahydrate is the form in which the battery manufacturers want these cathode precursor materials to be delivered in. Now, there's a lot of discussion at the moment, and once again, this is hard to predict exactly where it's going. But if you look at the number of people actively checking out the possibilities of trying to resulfidize the ferronickel production in order to make a nickel matte, from which it's obviously easier to make a nickel sulfate, it's quite surprising to me. You know, if you look at the environmental implications of avoiding sulfur in smelting, to me it just seems completely wrong to think of why would you deliberately introduce sulfur into the smelting stages of the process. But there are a number of studies ongoing at the moment amongst most of the big mining companies around the world looking at exactly this. The largest producer of nickel pig iron, a company called Tsingshan, they have declared their intention to do just that, all the way from nickel pig iron. So you've got vast quantities of iron that you're also going to have to sulfidize. And to me, environmentally, this just doesn't make any sense at all. And it flies in the face of the environmental advantages of electric vehicles. So I'm kind of skeptical as to whether this really makes sense. But right at the moment, the market drivers are significant. There's a very big premium to be paid for the nickel sulfate product. And so this is attracting people right now. But one has to look at it more holistically and say, well, what is the additional cost for environmental cleanup that's required for the introduction of sulfur? So all of those things are being looked at the moment. There is a preference, obviously, for the higher grade nickel or the nickel with sulfur associated with it, simply because that makes it easier to produce the nickel sulfate. And so, yes, that is driving demand. But again, you know, if you look at the actual quantities of nickel used in batteries right at the moment, it's about 5% of production compared to, say, 70% for stainless steel. Or if you take into account the additional other steel alloys, you know, you're talking about 86% of nickel being used to make steel-based alloys of one description or another. And so batteries are small, but the growth is incredible off that small base. And people are projecting that it will go to maybe 30% over the next decade. That's a massive growth. And obviously that's going to require lots of new developments happening. So nickel is quite an exciting place to be right at the moment.
Yeah, it reminds me a little bit, I mean, if you read and follow the vanadium story and, you know, the nickel battery story, and you see what's happening, you know, the minute the palladium price goes up, people start substituting back to platinum, and they substituted palladium with platinum because palladium was too expensive. So there's this, I really enjoyed your comment about the fickleness of the market. It's probably in all these battery and renewable energy kind of potential metals are so exciting and really unpredictable. That's about all I can say. And while we're talking about it, I think I have a first for a webinar. Actually, I have a WhatsApp question from somebody who wanted to attend but couldn't attend. So they're asking me to ask you if you've had some thinking about using hydrogen in the pre-reduction of nickel. What do you think the potential for that is?
Yes, it's something that needs to be studied. It's something I'm not aware of from any first-hand experience, obviously. But yeah, the potential is enormous. But the carbon usage in ferronickel smelting is really, you have to look at two separate contributions there. The one is simply the amount of energy that is required. And of course, the world at the moment still is based largely on carbon-based forms of energy, but that's going to change. So in a sense, you've got to separate that out from the inherent reduction requirements of carbon, the chemical use of carbon rather than the energetical use of carbon. A lot of the energy that goes into ferronickel production comes simply or goes into the removal of the water that's associated with it. And yes, obviously you have to melt it and take it to high temperatures as well, and supply the energy required for the reduction reactions. So nickel is one of the most demanding when it comes to energy usage. But the amount of reduction that's taking place is in fact relatively small. One of the things that makes nickel production, along with that of platinum, quite different from many other metal smelting operations, is the fact that you make very tiny quantities of metal when you smelt these ores. Say 10% of the metal of the ore coming in lands up as your metallic product. And that's much, much lower than most of the other major metals. And so the amount of chemical reduction that's taking place is in fact relatively small. So yes, should people look at hydrogen for nickel? Yes, they certainly should. But probably if you had to make a choice, you should look at it in steel far more vigorously than you should in nickel, because that's not the major driving force for changing the world right at the moment.
No, I mean, the impact on iron is very, very big, whereas nickel is probably not. But it is probably, it's a very interesting thought experiment question, I thought.
Yeah.
So it is, if you read everything, it's about iron, carbon-free iron, and you see the news articles being published. So hydrogen is definitely coming to the forefront, but I think it's also alternative reductants. And there's clearly, all of the laterite smelters need some kind of pre-treatment process. And there's definitely some opportunity to shrink your carbon footprint dramatically in that aspect.
Yeah.
So I think we've focused on Valdeni's questions. I'm going to just skip one and go to a question on nickel pig iron. If you are aware of any new projects, greenfields or brownfields, for expansions with ferronickel, excluding nickel pig iron.
Yes.
Are you aware?
Yeah. I don't know how many of them have been publicly announced or anything, so I can't really say very much about it, sort of listing them by name. But am I aware of them? Oh yes, they are certainly happening. I think there are a number of new plants coming on stream at the moment as well that are well known, but I'm presuming you're talking beyond the existing ones that are already coming, that have been in the pipeline for some years already. Yes, certainly there are people looking at this very seriously, and they will need to. If these projections of nickel demand for battery growth alone, ignoring the growth, the expected growth in stainless steel, we are going to need a number of additional new major nickel smelters every year. Basically, we're going to need to see something coming on stream.
Yeah, I agree that there's definitely projects in the pipeline that is probably not formally announced yet, but there's definitely movement.
Yeah.
See, Franciscus asks if you could just explain the essential difference between ferronickel and nickel pig iron processes.
Yes, okay. Effectively, the history is perhaps a little different. The nickel pig iron started off in a blast furnace, but I think like everything else in the sort of generic ferronickel production, it's moved to electrical production. And in principle, there's really no inherent difference in the type of vessel that's required, the type of process that's required, whether you're making nickel pig iron or ferronickel itself. It's essentially a question of degree. If you're making nickel pig iron, you simply have to add more reductant. You have to reduce more iron into the metallic form, and that requires more energy. And that's effectively really what it comes down to. You have some small benefits in the fact that when you reduce more iron, you will have a better recovery of your nickel that's present in the ore. But obviously your transport costs go up significantly, your operating costs go up significantly, and you don't always get rewarded for it as well. So one of the things that I found very interesting in trying to look at the distinction between ferronickel and nickel pig iron is that there are very few, essentially there is a very high concentration of nickel pig iron producers only in China and in Indonesia. And the ones in Indonesia are essentially being funded by Chinese stainless steel producers. And every one of them is linked directly to a stainless steel smelter. So nobody out there produces nickel pig iron and ships it onto the general market up for sale by all comers. Effectively, it's a captive production. So as part of their iron production, they're simply using nickel ores as a source of iron as well as the nickel itself. Anybody else who's in the more general business of producing a commodity for sale is making ferronickel of one grade or another. And again, it's a fairly arbitrary cutoff point that I chose, but it's fairly widely used to say, well, below 15% nickel, we'll call that nickel pig iron, and say in the 15 to 40% nickel content, we'll call that ferronickel. But yes, that's my understanding of that distinction.
I remember when I started working at Mintech, some of my first projects were all ferronickel, so I'm very fond of the topic. But we started working, and it was almost a hard and fast rule that 25% is the minimum grade. So that's ferronickel. If you go below it, then you're in trouble, and you have to do something to the ferronickel, either blow out some iron, upgrade it to 25%, because that was regarded as the market acceptable level of the lowest grade. So everybody was hunting for high grade, high iron to nickel ratios, because that's ultimately what determines what you can make. But as the world is always going increasingly, and there's less and less cherry picking being able to be done, this trend happened. And it was a very interesting flip this 15 years ago, where people said, well, we've got low grade stuff, we may as well go the full hog and make a low grade thing and live with it. And it became an entire new business in our lifetime. And it's for me always fascinating how this evolved, and it tied directly with that massive growth in steel production capacity in China. So it's definitely a force to be reckoned with, but an interesting history and a very unique story. So the next question is perhaps by introduction, ferronickel is generally produced, as you said, in circular furnaces and rectangular furnaces, typically with sort of a shielded arc approach. The arc is open, but it's covered by bath. And then Paul O'Shaughnessy is asking us if you could elaborate a little bit about Mintech's role in the pilot testing and commercialization of DC smelting for ferronickel, which is an open arc process, and it's currently, we know it's commercialized in Russia and New Caledonia, and what Mintech's role was in that process.
Yeah, so certainly I think that's been a very, very interesting story. Mintech got involved really in the DC arc development, or the development of DC arc furnaces, actively from about the 1980s, was trying to commercialize that technology for ferrochromium production. The 1990s saw it going into ilmenite smelting for titanium slag. The early 2000s saw a range of other applications, including recovery of cobalt from other non-ferrous smelting slags, and many other applications along the way. But it was probably the late 1990s where Mintech was approached by, at that time, Falconbridge, to investigate a process route that involved DC arc smelting, as well as fluid bed reduction for the upfront portion of nickel laterite smelting. And so a lot of development work was done in that time. a lot of deep thinking was done as well, really trying to understand the fundamental complexities of what was happening inside the furnace. It drove a lot of the in-depth research as to the nature of the electric arc and its interactions with slags and the electrical properties and how furnaces are designed. And of course, their particular interest was the Koniambo project in New Caledonia. And of course, over the time span of that project, the company that we were dealing with moved from Falconbridge to Extrata to Glencore. So it was the same people, the same project, the same mine, but the name of the owners changed quite a lot in the meantime. Because that project was envisaged to be a very large project, one of the biggest in the world, it was necessary to have a look at twin cathode supply of electrical power to the furnace. Simply the largest of the pre-baked graphite electrodes that were being produced weren't enough, didn't have sufficient current carrying capacity to drive the amount of power into the furnace that was required. And so a lot of work was done on the interaction between two arcs being generated by these twin cathode configurations. And of course, we found that the arcs are actually attracted towards each other, towards the center of the furnace, which is a desirable property from the point of view of containment of the furnace. So much work was done on the electrical behavior, the arc behavior at that time, as well as the chemical behavior and the reduction behavior and feeding of hot materials into the furnace. But then effectively, the development of the process kind of got to the point of being well established, well piloted, and then went into a quiet period for over a decade, probably a decade and a half, while all the other infrastructure had to be built in New Caledonia. And one forgets that because nickel laterite deposits usually are located right in tropical, undeveloped, very inaccessible parts of the world, most of the expense of the project is really in setting up the infrastructure. So anything from roads to ports to power plants, all of that had to be developed and built before one could get to digging out the mine itself, and then only the smelter after that. So a lot of work was done. And it was an interesting development. Obviously, we were waiting with great anticipation to see the full commercialization of the technology for nickel laterite smelting in a DC arc furnace. And so the principal developers, it took a while to get such a big project off the ground, and a smaller project in Russia actually implemented DC arc smelting for nickel laterite ores before the Koniambo project got up and running. So that's the sort of brief history of Mintech's involvement as far as that went.
That was a very interesting history. We all watched, and we were sort of mostly not involved in the last part. Building harbors and hospitals is not part of what Mintech did. But thank you very much for that, Rodney. I think it is quite an interesting history. I've shared the link where all Mintech's related nickel papers can be found for the questions that came up about the references. So also welcome everybody to go and look at Rodney's papers. There are several that are not just nickel, but worth reading as well. Highly recommend it. I think the last question, we have 2 minutes, is about whether a ferronickel ratio of 8 is actually processed industrially. I think the second question is probably how much nickel is recovered from slag sources, probably like dumps, but I'm interpreting. If you can just, so we know that the iron to nickel ratio of 8 is probably nickel pig iron.
Yeah, if effectively you've got that trade-off. You've got to characterize the deposits and then see what you can do with it. And then it'll be an economic question. So it's going to depend on things like where is it located as well. That will determine whether it makes sense or not. If it's very far away from your end user market, it might not make sense to make something that's very, very low grade of nickel in the resulting alloy. But the overall costs of processing is obviously going to depend not only on the iron to nickel ratio, but on the actual grade of the nickel in the ore as well. So the iron to nickel ratio is going to determine what the relationship is, as we showed in one of the graphs, between the grade of nickel that you can produce and the recovery at which you can produce it. And so, you know, you might get a situation where you can mine the ore cheaply enough and perhaps the overall grade is high enough that the iron to nickel ratio doesn't matter all that much. You can still produce an acceptable grade, and as Isabel said earlier, the level of acceptability has become much wider over time. Effectively, the fact that China produces more than 50% of the world's stainless steel, and that's really the primary outlet for the ferronickel, and they're quite happy to take in nickel pig iron. So you know, whatever grade of ferronickel you produce, there will be a home for it. And it's just a case of saying, well, at what recovery of nickel can I actually get? And that's an economic trade-off. So it's a bit of an evasive answer, but in the limited time, that's probably
yes,
what we can manage to
always
do.
Extra post-tapple processing, you know, that there's plants where they do actual converting, blowing some iron out, and then you have a nickel losses to the slag that needs reprocessing. So it's always complicated. But it's time for us to, again, thank you so much. And again, congratulations. I've shared the picture of the award to the chat, so anybody who can see that. And as always, Rodney, it's been an absolute pleasure chatting to you about pyrometallurgy this morning. I hope the participants enjoyed it as much as I did. And hope we see you soon for another wonderful session.
Thanks very much, and been lovely to talk to everybody today. Thanks.
Thank you.